Thank you. Okay, so this is going to be a long talk, so please bear with me. I'm going to start slow so we could hopefully be all on the same page. So I'll start off by saying a little bit about kind of the general state of NLP, because what I want to do is I want to talk to you about where we want to go, right? Where we are right now and what we want to do and what we can do about it. So we'll start with a bit of history and a little bit, like a very quick primer on, what people have been doing in NLP. And then I'll talk about where I think we're going to go soon, hopefully. And I'll talk about a couple of projects that we're doing in my lab to get there, okay? And also, if I speak too quickly or if you want me to slow down, please just tell me, okay? Sorry? Okay. I'll try. All right. Okay. So what we want to do is we want to develop computational models of human language, right? So we want to be able to interpret and generate text the way each and every one of you can do, hopefully. And we want their models to be as good as humans, right? We want them to be able to do the same things or better, to be as good or better. We want to do comprehension and reasoning and inference. We want to do fluent dialogue. We want to be able to do all these things that humans get tired doing, like extracting information and summarizing content and also answering questions, translating, all these things. We also want to be able to do, all these meta things that humans are decent at, like humor and irony. And some people are better at it than others, but we want our models to be able to do that. And so, all of these things are basically a part of intelligence, right? And if we're emulating intelligence and building artificial intelligence, language has to be a part and parcel of that. So a few words about where NLP started, right? So NLP started with a few prominent mathematicians in the last century, right? So people like Claude Shannon, who I'm sure you guys have heard about, who was working to estimate the entropy of human language. People like Alan Turing and Jack Good, and they worked on statistical modeling of language. The idea was to kind of estimate the probabilities of sequences, and all of that was in service of breaking the codes the Germans used during the World War II. And then people like Warren Weaver, who was working on machine translation, back in the middle of last century, and saying things like, I'm pretending that the text in front of me is really just written in English, but it's encoded so that it's in Russian, and I'm going to have to come up with some methods for decoding it. So all of that was great, but these people, they made a lot of promises, and these promises kind of fell flat. For example, they promised machine translation by 1954. Never happened. So what happened instead is this sort of gradual progression. So in the 60s and the 80s, that period of time, people were building mostly rule-based systems, which is, if you take an average computer science person, you sit them down, or they don't know anything about machine learning, they would sit down and code up some rules, right? So that's basically what people were doing. So you'd see a lot of finite state methods and rule-based context-free grammars, and these would be coded up and used to process language. So then, starting around 1990s, there was a sort of first revolution in NLP. So coming mostly from speech recognition, all these statistical models came into the field, and people started, instead of coding out the knowledge needed to process language, they started to basically do something else entirely, which is annotate some language, annotate some text, and then use their statistical models to identify patterns in language automatically, right? So instead of coding out the features, instead of coding out the knowledge, you would basically create a way to represent your linguistic input in terms of features, so-called features. And then these features would be used to represent your examples in text. And then you'll use methods like support vector machines or hidden markov models, standard multinomial logistic regression to basically do classification and generation and things like that, using the input that was generated based on some representation of text. Okay, so then roughly in the past, I want to say 7 years, no, it's closer to 7, sort of yet another revolution started happening, and that was sort of the methods of the so-called deep learning coming into the NLP, mostly from computer vision, but also from ASR, automatic speech recognition. So the idea was now, instead of building these feature representations for your input, instead you would let your models learn these feature representations. So your representations for examples, linguistic examples from text, would be these multidimensional vectors, which would be learned by the model in the process of learning to classify text, for example. Okay, so this is roughly where we are now, and I'll walk you through this a little bit because I know there's kind of difference in where you're starting today. Okay, so here's a very quick primer on sort of the feature representations, right? So let's say you have a sentence, our waiter was rude, and your goal is to identify whether this is a positive sentiment or a negative sentiment, okay? So a feature representation, a typical feature representation would do this. It would basically track the words that occurred in that sentence, right? So imagine a vector of dimensionality of your vocabulary, and then it's mostly zeros, but there's ones in positions that correspond to the words that actually occurred here, right? So you'll have, you know, one under hour, and one under waiter, and one under, thank you, and one under was, and one under rude, right? And then you have some other features like, is there more negative words than positive? And that'll be also like a binary feature. Is the sentence in the present tense, right? So as a result, you get this binary feature vector. It didn't have to be binary, but that's roughly how you would represent this kind of sentence. And then that would be provided as input to your model, which will do classification. Okay, so so now what would you do in terms of input and processing if you had a neural network instead, right? So I'm assuming you guys have seen neural networks by now. Is there anyone who hasn't? Can I have a show of hands? People who have seen neural networks. Okay, good, excellent. All right, so basically you have some input, right? And then you apply some linear transformation to that input. And then you apply some non-linearity, some non-linear function like sigmoid or hyperbolic tangent, or just a rectified linear unit. And you perhaps repeat that several times, so you have a model with a number of parameters. Your parameters are basically matrices, and you're going to set those parameters by basically using gradient descent. So you're going to have some objective function, and you're going to backpropagate your gradients to set the parameters to optimal values, hopefully. Okay, so so at the moment, up until very recently, sort of sequence processing of text was done with, or is being done with recurrent, so-called recurrent neural networks. So the difference between a regular neural network and a recurrent neural network is very basic, and the difference is you have this recurrence, right? So you're reading in a sequence of words, and each word is provided as input at that time step, and also as another input at that time step, you get the previous state of the model, right? The so-called hidden vector, okay? So your hidden vector is a function of this linear transformation of the inputs, and the inputs are, you know, your representation of the word, and the representation of the previous hidden state, h sub t minus 1, okay? Okay, so you basically continue reading your input, updating the state, hidden state recursively, and the way you would train these networks, and here I'm assuming that there is some kind of output that your model is producing at every time step, right? For example, maybe it's a label, maybe it's a part of speech tag that you want to attach to each word, okay? So the way you would train them, you would basically unroll this recurrence, right? So your computational graph would look like this. And then there'll be your input. You produce some output. You compute the loss function based on the output and what you were supposed to get. And you do this for all the time steps, so for all the elements of your sequence, okay? And again, you do this similarly to a regular neural network. So you would take all these losses that you computed, loss functions that you computed, and you would backpropagate the gradients through a computational graph to update the weights. And you would basically just update these weights until you get to a reasonably good performance. Okay? So good so far? Okay, cool. All right. So, all right, so we're reading these sequences of inputs. We can do various things with them. First of all, we can accept inputs of various sizes, right? In other words, instead of accepting fixed length vectors, we can now accept these sequences. And they could be variable length. So we could accept a sequence of a certain length and then output a single output, right? So that would give you classification or regression. Or you could perhaps generate things. So if you're thinking of machine translation or dialogue, you accept a sequence and you generate a sequence, right? So this is what's usually lovingly referred to as sequence-to-sequence models. A couple of additional wrinkles in case you haven't seen them. So typically, instead of just using regular RNNs, people now use these gated cell memory units, which have a little bit of additional machinery so that instead of endless multiplication of matrices, you actually get additive update here. So that helps with gradient propagation. So you avoid gradient explosion or gradient basically right. So okay. So because we're using these units that have some additive mechanism inside of them that allows them to persist across multiple time steps, we're able to learn slightly longer dependencies for these long sequences of text. And remember that language typically would have long sequences of text, right? Okay, so then what you do is inputs. On the diagram I just showed you, I was using the so-called one-hot encoding, right? So I have the vector dimensionality of my vocabulary. It's basically all zeros except one position which corresponds to the particular word, right? You don't necessarily want to have that. You want to have some more meaningful representation for your vocabulary. And typically what you see now is people using so-called pre-trained word embeddings. So here's an example of a pre-trained word embedding model that has been very commonly used since 2013. So what it does is basically you're computing a probability of a word. You're expressing a probability of a word as a product of the probabilities of the words to the right and the words to the left, okay? And then you express them using softmax. And these are going to be your embeddings. These vectors U and V, they're going to be your embeddings, okay? And so you're going to train, these are going to be trainable parameters. You're going to run this through all of the examples in your huge corpus, and you'll obtain the values for these vectors, which will be fixed embeddings for your words, okay? And of course, when you use these, so when you go back to your recursive neural network, you can use them as inputs here instead, right? And you can also continue training them. In other words, continue updating the weights as you train your classification model or your regression model or your whatever generative task you're using, okay? Okay. So what you typically get is you're reading this input sequence, right? And if you're using this type of model for a generation task, you get a hidden representation at the end of your input. And then you use that basically summary of your input that your model has produced to generate a probability distribution over your vocabulary at each time step. And that allows you to generate something word by word, right? So if you look at this type of configuration, here, whoops, sorry. Okay, so you've read in your input, you've updated your hidden state vector. So this assumes now that your model has been trained, right? So you've learned those matrices, right? And now you're just running through some input to get some output, okay? So you're reading a vector representing the incoming word at each time step, and then you use that input together with the previous hidden state, which is also just a vector, right, to create the next hidden state. And at the end of that process, you have a summary of your input, right? Your h sub n, your hidden vector. And then you start generating the outputs, right? So at each point, you use that hidden representation to generate a probability distribution over your whole vocabulary, right? So you take a vector of the dimensionality of your vocabulary, you softmax out over it, and you get a probability distribution, and you sample from that probability distribution to generate a word, okay? And then you feed in as input to your decoder whatever word you have generated. So this is what's lovingly referred to as encoder-decoder architecture, and I apologize to those of you who know this backwards and forwards, but just so that we'll be all on the same page. Okay. Any questions so far? Pretty straightforward. Okay, good. All right, so just a quick demo of what these types of models can do. So this is a very simple dialogue model that was trained on movie dialogue corpus, and literally trained with just input and output, right? Like input message, response, right? So the pairs. And this one used learned word embeddings as opposed to pre-trained ones, and we use 50% dropout between the encoder and decoder, and you get interactions that look roughly like this. So, hi bot, hi I'm busy. Well, that's rude. It's okay. So this side is the bot, right? This is the human here. Okay. What are you talking about? Okay, how are you doing today? I'm going to miss her, right? So it looks roughly coherent, but not really in terms of the overall flow of the dialogue. But it's not bad, considering it's really just training on pairs of messages, right? So, and this kind of thing you get basically for free, right? You train your encoder-decoder architecture with nothing else, and you get this, okay? So that's pretty good. Okay, so, but of course there are problems, and the problems are also known, and they are, you're actually summarizing a whole sequence as a single vector, and then you're trying to use that vector to generate the whole new sequence, right? So you're basically limiting how much information you can retain from your input. So a solution to this was to use so-called attention, which is basically just using the whole input sequence at every time step in addition to your hidden layer representation. So what this would do is basically at every time step, your hidden layer would be used to compute a distribution over the input, okay? And then you would weigh your input from the input matrix, and that will be fed into the generative model at the next stage, okay? So that way you basically have a summary of information from the whole input as well as your processed digestion of the input in the hidden layer, okay? Okay, and if you've been following what's been going on in the past year or so, you'll also notice that there's been arguments that you no longer really need these recurrent models. All you really need to do is just have this attention over inputs and maybe process it multiple times. So if you look at the transformer model that was published last December, for example, instead of using the recurrent inputs, they basically have several rounds of attention over the full input sequence, and it's applied encoding time to produce a representation, and then, so this is basically self-attention for every word. So every word, you produce a representation for every word by combining representations from the words in its context. And you do that multiple times, so you have multiple layers of processing. And you use positional embeddings to let your model know which portion of the sequence your word is actually coming from. okay? And so then you have decoder, and the decoder has information that the encoder has provided, the encoding, and then also whatever it has generated to this point. Anyway, so all of this by way of just background on the kinds of things that people do to solve generative problems, right? Where you have a sequence transduction, so-called problem, where you have a sequence that's input and you're producing a sequence output. So these are problems like, so these are problems like question answering. You have a question and you produce an answer. Machine translation, you have an input, you produce a translation. Dialogue generation, you have an input, you produce a reply to the input, and so forth. Okay. So the next question is, if we're doing so well, why do we need anything else? And what exactly that we're missing still? So I would argue that we're missing several very important things. First of all, our ability to learn long-distance dependencies is super limited with these models still, despite, even if you use attention over the whole text, right? So for the recurrent models, the main argument was, okay, well, if you're using gated memory, you're alleviating the problem with capturing long dependencies, to some extent, but still, you're not going to be able to do anything useful beyond maybe a sentence or two. And if you start processing sequences of text that are longer, you're not going to do very well. So attention alleviates some of that, but not entirely, and also has sort of limited scope because you're not processing what you're reading in the same way a human would, right? So you're not integrating the information that you're deriving from text in any way, shape, or form. What you're doing is just going over the input with your attention, right? The second issue, so that's long-distance dependencies, right? With attention, we have this way of mimicking what humans do when they read, but it's a very limited way of mimicking it, right? Because we're not really integrating what we've learned, right? So the second thing is related to this, and that's knowledge integration, right? So if you're a good human, you typically have a lot of stuff in your head that you're able to remember and use, right? And if you've known someone for a while, you have some shared context that you're going to retain from your interactions with them, and you're going to be able to use that, refer back to it. You'll be able to update this knowledge very easily, right? And that's going to shape the way you reply. So if you're building a chatbot, for example, and your chatbot is mimicking a human, right? It has to have this whole history shared and represented in some way, and it has to have it updatable in some way. So that's not happening yet, really. So things like Wikipedia and other kind of external databases of knowledge, there are ways to integrate them into your models, but they're questionable. I mean, people use regularization, for example, to integrate some of these facts from external knowledge bases. The other solution that may be relevant, and we're going to talk about it today, is external models with external memory components. And I'll talk a little bit about the limitations of them and what they can and what they should be doing. And finally, one thing that we're not doing so far, we're building a lot of models that are very task-specific. And some of our models are pretty good, meaning they are doing as well or better than humans at some tasks. Like if you've been following computer vision, for example, you'll know that some image recognition tasks, right, the current models actually outperform humans. Okay, great, we solved general intelligence. Not really. So we're missing this very essential thing. We're missing an integrated ability for realistic language processing. We want to be able to support things like reasoning, other high-level functions. And if you looked at, for example, the memory models out of Facebook, right, so they haven't really, I mean, there's been a lot of kind of hype about them, but they haven't really been applied to real-life text. For example, if you've seen the so-called Bobby data set, people who have seen it? Okay, so what do you think of it?
It's very easy.
It's not language, right? It's very restricted. It's an analog of, the toy worlds of the 1970s, really. So these haven't really been applied to the full extent to the actual live, noisy, and unpleasantly noisy, and horrible and hard to process language. Okay? And yet humans are pretty good at it. So the other thing that's not really happening is we're not attempting to model kind of the neurobiology of language or the functionality of language. I mean, we know quite a lot about how humans process language. There's a lot of data on that. Our models are not aiming to do that, and I think we're losing out by that because what we're building is not going to be able to do what humans do. So, well, I'm gonna skip these. There's some of the work in these directions from my lab, but we will talk about some of them. But let me tell you. So, the two projects I want to talk to you about deal with two of these problems. So the first topic I want to tell you about has to do with mimicking some of the things that we know about the brain. Okay, so the idea is, for the first project, is to see if we could learn a modular representation of linguistic input that mimics functional specialization in the brain. I'll tell you what I mean in a second. So the second topic will have to do with a particular problem that requires the knowledge of long-distance dependencies and text-wide context as applied to a specific problem of extracting event timelines from text. So understanding what happened, when, and in what order. And I'll show you a memory model that we came up with for that. And I'll argue that this is roughly the direction we want to go. Okay, so let me start with the first project. So this is, how many of you have seen generative adversarial networks? Excellent, okay. All right, so here's the motivation for this project. As I said, we want to model this human-like learning at this micro level of human neurobiology. And I don't mean necessarily emulating how neurons work in the brain, right? Because we're still building these black boxes. But there's a lot of interest recently in the machine learning community, the deep learning community, for trying to come up with computational mechanisms that try to emulate some of these micro behaviors in the way cortical columns in the brain, for example, are activated, right? So you might have seen some of these. So Hinton's capsules models. Anybody seen those? Good. Equilibrium propagation from Yoshua Benjo's lab. So there's a lot of interest in these. So this is kind of trying to emulate the learning at the micro level, right? What happens when neuronal pathways are strengthened, right? How does human brain learn? And can we emulate that? So the second part is the macro level, right? So these are kind of general principles of intelligence, right? So we know how humans learn to some extent. We know that there's imitation learning, right? I don't have to get kicked every time to learn something. I can just see somebody else get kicked, right? And then I'll know not to do that, right? So imitation learning, planning, right? We know humans plan, prediction, these kinds of things are very general ideas about how human intelligence works. Well, guess what? We also have some idea for how language processing works, generally, right? For example, we know there's semantic priming. How many people have heard of semantic priming? Okay, good. So this is basically the idea that when you're processing a sentence, at any given point during that sentence, you have a lot of different senses, meanings activated. And these meanings do not get focused and fixed until you get to the end of the sentence. In other words, there's some activation pattern in your brain that allows you to kind of delay disambiguation until the end of the sentence, right? So we know that that's true. We know a lot of other things like chunking, right? So as we begin to use some concept, we pull together lower level descriptions, like when you learn something, right? You start to be able to operate with very high level concepts very easily, but for that you need to chunk what you've learned, right? So in other words, if you do, whatever, matrix multiplication, you don't get to every time review how to do it, right? You're just gonna know it. So, okay, so that's great. So we want to we want to have some models that are able to do these things, and we don't. So the other property that is what we're concerned with here is the so-called functional specialization of the brain regions that are related to language processing. And you may have heard, if you've done any neuroscience or any psycholinguistics, about these grammatic and semantic aphasias. So these are speech impairments in patients who have had lesions in their brain due to some disease, okay? So there's two areas in your brain, Broca and Wernicke, that are associated with, well, there's more, but at least these two that are associated with language processing. So people with lesions in the Broca area, this blue blob right here, are what's called the expressive aphasic. So they can't form grammatical sentences, but they're able to comprehend, right? So they speak very telegraphically. So, you know, if you're asking me for a pen, you would say something like pen, write, give, right? But you wouldn't be able to put it together in a sentence. But you would understand what I would say. And then people with lesions in the Wernicke area can actually produce connected speech quite well, but they don't necessarily comprehend. So they would very often come up with kind of empty, but grammatically correct constructions. So also, you know, if you look at linguistics work, linguists have modeled form and meaning as separate for a long time, and now there's quite a bit of a debate in neuroscience whether this functional specialization actually means what they thought it means, which is, okay, you have, you know, separate semantics and syntax, and can you have those? Nonetheless, it's clear there's some substantial degree of modularity in the way language is processed in the brain. So the question is, can computational models support this representational modularity that mimics that to some extent? So that's what was our question here. Okay, so for example, can we represent something like linguistic register separately, right? So, so linguistic register is a subset of language where you would use only certain type of expression in different, depending on the context, right? So, you know, if you see a friend, you can say, okay, yo, what's up, right? But you would not say that when you're coming, you know, to a bank to get a loan. You would instead say, hello, how are you, right? So these are different ways of expressing yourself depending on the social context. These are called social registers. So the question is, can we kind of learn to distinguish between these and produce different text, different language, depending on which register we want to imitate, okay? So in this case, we were using newspaper headlines versus scientific article titles. So clearly different style. Another possibility is, okay, well, what about different diachronic slices of language, right? So if you compare, for example, original Shakespeare versus Shakespeare translated into modern English, you'll see that there's quite a bit of difference because, you know, Shakespeare wrote in early modern English and now we're in contemporary English, and so things like what would she have would actually mean what does she want, right? Okay, so can we do that? Can we translate between these two? Can we learn a representation that will tell us to what extent a particular expression belongs to one slice or the other? And finally, you could do something else like sentiment, right? Negative or positive polarity. Can you learn some sort of representation that allows you to modify that? Okay, so here's what we want to do. We're going to learn two encoders. One that takes an input sequence and produces a meaning embedding, and the other that takes, whoops, sorry. That's right. All right, I'll just keep this here. All right, and the other that takes an input sequence and produces a form embedding, right? So we're going to train a model, we'll call it generator, that will take that encoding and produce an output, right? So an encoder will produce two encodings, a generator or decoder will take these two encodings and produce some output, okay? And so really what you want to be able to do is you want to be able to swap these and see whether your model can swap them, right? So take in, you know, yo, what's up? and produce hello, how are you, right? So swapping the representation. Okay. So the inspiration for this particular limitation that we had comes from two sources. One is the style transfer work on images. How many people have seen that? Okay, great. So we can go through this very quickly then. Okay, so clearly, if you want to test whether a separate representation is learned for this form or style, is you're going to want to decode from a combination of meaning and form from different sentences, right? So this work is pretty similar to the kinds of things people try to do with style transfer in computer vision, where you take, for example, a photograph, you learn a style on another painting, for example, Van Gogh, and apply that style to a photograph to produce a Van Gogh-like rendering of that photograph. There's been surprisingly little work on that in text for a variety of reasons, not least of which is that text is discrete and it's much harder to learn these things. So some of the approaches that people have tried involve actually using parallel corpora, right? So you have two texts that mean the same thing, but are written in different register or written in different language, right? But that's kind of limited, right? Because you're only going to have that for particular types of task. And then there are approaches that don't require parallel corpora. Like there's a couple of approaches that we're trying to use variational autoencoders to do this. And a couple of GAN-based approaches. And a variational autoencoder is just an autoencoder where instead of learning the representation, you learn a distribution, and then you generate from that distribution. Okay? All right, so surprisingly, no prior work actually attempted to learn separate embeddings for the form of each input outside of either learning this kind of single representation for style, right? Or just flipping one bit in their model to change between two styles, which is not really realistic because if you think about it, it's usually a mixture, right? Like when you speak, you don't speak in a single style, right? You mix them up. So each expression that you say will be to some extent in one register and to some extent in other registers, right? So it stands to reason that you want to have a separate embedding for style or for form for every input sequence. So that's exactly what we're trying to do here. Okay, and the second inspiration is, as I mentioned, from adversarial learning. So if you haven't seen that, here's a very quick recap. So this was proposed in 2014 and also similar to some ideas from Schmidt-Huber and work in 1992 called predictability minimization. As a side note, this is a kind of in-joke in the deep learning community that kind of any new model that people come up with has been invented by Schmidt-Huber in the early 90s. So the idea is you have two neural networks, the generator and the discriminator. The generator's objective is to generate realistic-looking examples. And the discriminator's objective is to discriminate between the real and the fake ones, right? So they're working in opposition. They're adversaries. Okay, so here's a very nice illustration of this from Cristiati. Think of a criminal that's producing fake money. That's your generator, and a cop. And the cop tries to distinguish between the fake and the real money, right? So the criminal's goal is to maximize the similarity between the fake and the real, and the cop's goal is to detect the counterfeit money. So this is basically enough for you to build a generator with a adversarial network, right? So this tells you what the objectives should be, right? What do you think they should be? Right, so one should be perhaps just a classification objective, right? And the other should maximize the similarity, right, between the fake and the real. Okay, so this is your basic GAN architecture, right? So both the cop and the criminal are the neural networks, and discriminator is producing the classification, that is distribution over two classes, one real, one fake. So the generator takes as input usually a random vector, and it learns a mapping from that random vector using its parameters into your data space, right? The representation of your data points. And the discriminator takes as input either a real sample drawn from the real data or a sample drawn from the data generated by the generator. And it outputs the probability of that data point coming from the real data. So D is trained to discriminate between the examples drawn from these two distributions. And G is basically generating based on the input noise, and this input noise is usually Gaussian. And so G is trained to improve its generated examples to nudge D towards misclassifying generated examples as real, right? So the goal is to reach a rough equilibrium between the distribution of the real data and the generated data. And the way you do that is you basically use the gradients from the discriminator to train the generator, right? Does that make sense? In other words, if the discriminator makes a mistake, that's good, right? If the discriminator doesn't make a mistake, that's bad, right? So that defines your portion of the objective function for the generator that's used to update the weights for the generator, okay? Okay, so this is basically the formal definition of the objectives for each of the two neural networks, right? So the discriminator maximizes the probability of basically the standard cross entropy loss here, right? So we're maximizing the probability of the data drawn from the real distribution being classified as such, and maximizing the probability of 1 minus whatever the probability of the real of this example being real for the examples drawn from the data generated by the generator. Okay, and then the loss for generator is basically just again the cross entropy, except you take discriminator's classification of the input generated by the generator. Okay? And you train these with alternating gradient descent. And typically people would train, in other words, update the weights of the discriminator more frequently than they update the weights of the generator. But that's a general configuration for GANs, in case you haven't seen them. So we use the same kind of adversarial learning idea. So here's the adversarial configuration for the model I've been describing to you. We have an encoder and a generator, and we have a discriminator, right? So the encoder takes as input a word sequence. It produces two encodings, one for meaning and the other for form. And then the generator gets those and produces a word sequence. And so the generator and the encoder are trained with a standard reconstruction loss. So cross entropy, right? Word by word. And then you have a discriminator. The discriminator, its role is to encourage the model not to put any information about the form into the meaning embedding. So it gets as input a meaning embedding produced by the encoder, and it tries to classify, whether it's Old English or contemporary English, or whether it's negative polarity sentiment or positive polarity sentiment, whether it's informal register or formal register. So then you take that loss with the negative sign and use that to update the weights for the encoder, right? So that means that the encoder is encouraged not to put any information that's going to allow the discriminator to meaningfully identify the form from the meaning embedding, okay? Okay, so I'm going to skip some of the details, but basically these are a bunch of fully connected layers for the encoder. And we have an RNN for a generator. And they're trained, as I mentioned already. So So what we used, in fact, was not the classical GAN formulation, but the loss that was inspired by the Wasserstein GAN loss, which is very, very similar to what I described to you, except you basically remove the nonlinearity from the output layer and use just the output layer directly. So you're basically outputting real numbers instead of numbers in the probability distribution, right? So that means the discriminator is encouraged to output large negative values for one kind of form and large positive values for the other kind of form. So if you picture a sigmoid, you basically just remove that, right? And you get a real number instead. And so this loss is applied to the parameters of the encoder. And that's how you combine the losses. So the encoder generator is trained with the basic reconstruction loss minus the discriminator loss. And the training procedure is very similar. So you train each batch, train the discriminator, then train the encoder with this combined loss. Okay? So we conducted some experiments with this, and we found that it actually works reasonably well. But I don't know if you guys have been following, but there's this tradition. So some schools like Carnegie Mellon University and MIT, they have these fake conferences that students run, and they submit fake papers to these. And so there's this conference called SIGBOVIC from CMU, and in 2017 there was this very funny, hilarious paper published where they basically argued that there's too much network-on-network violence, and literally they proposed, instead of GANS, they proposed GANS, and that stood for Generative Unadversarial Networks. And the idea is you train two models, a generator that does its best, and then it captures the distributions it feels it can manage, and then a motivator that helps it to achieve its dream, Anyway, so we actually took this seriously, and thought, okay, well, maybe we'll do the carrot and stick instead of just stick, right? So to test this, we introduced this motivator component and motivational loss into the model. So here's the motivator now. And so the motivator's goal was to actually encourage the encoder to put the information about the form into the form vector. Okay? So it's very, very similar to what I've just described. Again, Wasserstein-style loss, except the motivator is a classifier that tries to classify form from form, right? So it's effectively encouraging the encoder to put some information about the form into the form encoding, okay? And so this is the full picture for how it's trained, right? So your encoder generator loss is now a sum of the reconstruction loss, because we want to be reconstructing what we put in, the discriminator loss with a negative sign, and then the motivator loss with a positive sign. Okay, so let me tell you a little bit about evaluation of this. It's a little bit tricky, as all generation tasks, evaluation is kind of hard to do. But basically, the thing that people have been doing is looking to see that there's some amount of content preservation, and then checking the sort of transfer strength, right? So the idea there is you train a classifier to detect a particular form, right? And then you encode a sentence, decode it with a different form, and then pass a generated sentence through the classifier and count how often the classifier can recognize the form that it was decoded with. Okay, so that's how they measure automatically transfer strength. And that's a way to bypass having to sit down a bunch of humans and rate your output, which is usually expensive, and humans are pesky. So, okay. And the content preservation was basically just a cosine similarity. And the tricky part is you don't actually want the content preservation to be completely extremely high, because it's unrealistic, right? So if you change from informal register to the formal register, you don't expect all the words to be preserved, right? That means you failed. So you want it to be reasonably high, but not super high. So here are the results, the DissoNet with Motivator and without the Motivator, compared to the previous baseline that we implemented. And you can see that generally Motivator either helps or it produces the same, for some cases it produces the same output as the DissoNet without the Motivator. But an easier way to see this is through visualization. So this is a t-SNE projection of 1,000 random sentences. And this is from the task with news headlines versus titles of scientific articles. And so these are meaning and form embeddings mapped in 2D. And you can see that the meanings are pretty much intermingled, right, in the space. And form, you can see the green points and the red points fairly well separated. So that tells you that presumably, if you trust t-SNE, the separation works, right? You're able to learn fairly distinct regions of space for the style while the meaning is not separated. So this is the picture without the Motivator, and it looks really reasonable. But this is the picture with the Motivator, okay? So this looked almost too good to be true, but we checked and it's true. So yeah. Okay, so that's the story. So these are just some examples, and you'll see that there's some changes that you get at the lexical level. This is comparing early modern English and contemporary English. Here's an experiment we did with, we took a bunch of questions from Quora, and the questions were of type how and what, right? So how questions and what questions, and then we swapped them. And so here's obviously cherry-picked example. We had two sentences. How can I reset a motherboard's bias password? And the sentence 2 was, what should I do to think positive? And so you swap the meaning and form, right? And you decode. And so what we got is, what should I do if I forgot the bias password? And for the second sentence, that was my favorite. How can I get self-esteem and confidence? So, all right. I'm going to skip some more evaluation. So here are some contributions from this particular model. We got competitive performance of several transfer data sets. Importantly, we treat the differences between linguistic form/style as continuous rather than categorical. Each sentence has a separate meaning representation, right? And this is in line with reality of language. We decode directly from the form and meaning representations of a sentence in the embedding space, right? Unlike the models that supply, there are some models that supply style information to do the decoding. And finally, we learn style representations without having to use parallel data. And yes, it's of course much better to do it when you have parallel data, because then your distributions are basically matched, right? If you're taking two corpora that are not parallel, you will have slightly different distributions, right? But nonetheless. All right. So, any questions on this so far? Yes? It's cross entropy. It's standard classification loss. Yeah, it's basically the same exact loss as you have for. So it's cross entropy with the nonlinearity moment. Sorry?
How many loss out of
So the reconstruction loss works on per word basis, right? Yeah. Meaning you're generating each word and you're computing cross entropy for each word, right? The discriminator and the motivator losses are classification losses, right? So it's binary classification, that's all. It's super simple, it's nothing sophisticated. Yeah? Yeah, these are publicly available. We didn't make them. Yeah. We definitely did not make them. Yeah, we haven't tried it on that. So, but yeah, cool. Okay, yeah, nice. All right, cool. Yeah, more questions.
I'm sorry, I didn't get it. Do you deal with the parallel data, or if there is no parallel data?
So this model doesn't need parallel data, right?
And how do you train?
So you supply the information of the source of the input, right, when you train. In other words, you know what the right classification decision is for each example.
So can you give an example, because you just
So
you missed this description that you have few different styles, two styles, and you should provide style information.
right, so for example, I think I gave them in the beginning. Okay, so basically, all of these examples would be used for training, right? For this example, if the discriminator assigns a higher probability to contemporary English, right, then that's correct classification.
Oh, okay.
That's it. Yeah, there's no magic. Just so the task for the motivator is exactly the same, right? Except you use it for the encoder generator with a positive sign, right? In other words, when the motivator does well, that's good. When the motivator doesn't do well, that's bad. And the same is this is reversed for the discriminator, right? So it's as basic as it gets. Okay? Yeah.
Diagram
of model, not yes. What force encoder put meaning in M vector? Why encoders can just put everything linear and style in F vector?
Excellent question, right? But then it's not using, it's using a smaller encoding, right? So presumably, yeah, it can technically encode everything in the form, right? But then it's losing half of the information that it can use. Yeah. Thanks for paying attention. All right, yeah.
Are there some thoughts about output of encoder structure?
What do you mean?
What it should be like?
So this is not an N. Encoder is just a simple RNN. It's not anything fancy.
So we are training encoder on output here.
So this part is literally kind of like encoder-decoder architecture, right? We're just adding some losses.
So we don't know what encoder should put.
So maybe if he replaces with whatever transformer, maybe it'll do even better. You know, it could be anything, right? Anything that produces an encoding. Yeah.
Encoder we put word sequences and get mean and vector, and then we put it in discriminator. But we will put into discriminator word sequences now, because the generator out of this word sequence.
So if you follow the arrows, right, you'll see that the discriminator just gets the encoding, right?
In images, we put in discriminator is image, fake image, and real image. In if transfer this into NLP, we will put into discriminator real sentences and fake sentences, but we put mean and vector.
So this is not exactly GAN, right? This is just using adversarial ideas, right? So we're not generating examples just that try to mimic the distribution, right? Instead, we're trying to push apart the representation. So it's not exactly GAN. That's why there's this discrepancy, right? Does this answer any question? No? So in other words, the question is, why aren't we providing the word sequence, the actual word sequence to the discriminator? The same way you would provide an actual image to the discriminator in GANS for computer vision. Is that the question?
And what's the generator loss and discriminator losses?
So the generator loss is a simple reconstruction loss, right? It's cross entropy on word basis.
This is special loss of input sequence.
Yeah, yeah,
It's an autoencoder.
yeah.
How discriminate help? This is just seq2seq.
Well, so discriminator, its function is to push away the encoder towards not putting the form information into the meaning encoding, right? Because we're using the discriminator loss to train the weights on the encoder together with the reconstruction loss, right? So the encoder is penalized whenever it puts enough information in the meaning encoding for the discriminator to do the classification correctly.
What discriminator?
Which type of text this came from? It's a binary classification. All right, yeah.
We already started to ask questions here. So basically, pushing to the limits, we can say that this part 4 should be dependent on the number of styles you want to encode in your architecture. So if you have 2 styles, it's sufficient for you to have very, very low dimensions in this hidden vector and put all the meaning in the M vector. So
Yeah.
if you have 2 styles, you can have dimensions of 2 or 3 style dimensions of 3. So have you done any experiments with different dimensions for these vectors?
With the size of it. So right, we haven't really done it to the point where we have conclusive stuff to tell you. But you're right. Depending on, so we want this to be continuous, but yeah, so what, right? If it's just a,
Actually, if you have 2 styles, extremely, you should have only one scalar here on F.
Yeah.
And to test if it works or not, it might be.
that's absolutely right.
Yes.
So yeah, and then you could check to see where they end up on a line, right? So, yeah.
Then you solve this problem with the meaning which can link through this F vector.
Well, yeah, I mean, you have to have a difference in dimensionality, right? It's just a question of how small you want to make it, right? So, yeah. All right, so we do have another project to talk about. I don't know if you guys are kind of ready? Okay. Yeah.
Sorry, one more question. Can we try this, or can we start with already pre-trained encoded model and just separate some intermediate representations of when we embedded our sentences, and then just use separated and believe that it'll be sufficient to base just a part of the embedded words of the vectors to discriminate.
So, I mean, we haven't done this, but I think an interesting thing would be to do to train an encoder to just produce 2 arbitrary vectors, right? And then, as you train, to map what happens to the embeddings you learn.
I mean, a bit different. You already have the encoded decoder architecture pre-trained, and then you just separate in proportion the vectors you have encoded, and feed one of these to the discriminators and the other to the motivators, and fine-tune them.
So, but how is that different from what I said? Sorry, I'm missing it.
All right. Then it's just
Okay.
So I have one more question.
Yeah, go ahead.
What do you think about possibility to use this approach to generate paraphrases? Because usually in dialog systems, real applications, we augment our data. And is it possible? So it seems that it's a very nice, it might be a nice solution for this problem if you train it on a variety of styles and then use it to generate paraphrase for the same meaning different styles. Then you can augment your data set, multiplying the number of styles you have.
So that's actually exactly right. We started this with thinking about paraphrasing, right? Because we wanted to have separate representation for meaning and expression, right? And of course, well, there's issues with that, right? Because you can't really have truly separate expression. But we did test it on MSRP. It did okay. It did better than some baselines. Slightly worse than supervised soda system. But so that to me says that it does work on that problem, right? Perhaps not as perfectly as we would like, but keep in mind that DissoNet is completely unsupervised, right? So, well, you give the type of input, the discriminator, but that's it. All right, so let me continue for a second. So this is great, but if you were listening closely, you noticed that we were basically trying to log the separation for quite a few very different tasks, right? Like learning sentiment polarity versus social register versus diachronic slice of language. These are quite different, right? So what other things can you separate out is an interesting question, which we haven't really thought about, but think about, let's say you're building a chatbot and you wanted to have a personality, right? Can you learn separate embedding for personality that would just produce this new style, right? And I think probably the way to think about it is, you think of personality as sort of a learned function that defines how you would integrate experience in memory and synthesize reactions, right? Whether it's appropriate to represent this as just an embedding that you apply in the set of a model, I don't have an answer yet. But it is clear that you do have to have some interface with some sort of persistent memory that you want your model to have access to. And this is what the second project that I was going to tell you about is trying to do. So presumably, we started with this idea that if you want to create realistic, generalist NLP model, right, it has to have certain properties. And maybe it should be able to separate out certain aspects of its representation. Maybe that's the way to go. We don't really know. But it's definitely true that you want to be able to acquire knowledge within a model, modify the acquired knowledge, and then use it to process stuff, right? At the very least, you need this kind of thing to at least resolve long-distance dependencies for things like text understanding and enforcing discourse coherence, where you need to know what things have been mentioned previously and what the answers were to the previous questions, right? So all of that requires this step of construction, which we haven't really talked about yet. So let me talk to you about this in relation to an application that does require resolving long-distance dependencies and does require global context in many cases. And this is the application of trying to extract the order and timing of events from text, right? So the goal is you get a text, and you have to create a kind of a timeline of what happened, right? And you need this information typically to do things like reasoning about the events, answering questions about what happened, summarizing what happened, right? So temporal reasoning, QA, summarization, all of those things really required to have some information about this narrative timeline. So here are some examples just to kind of get you thinking about it. Let's say you're an automated agent that's processing health records for human patients, and you want some questions answered, like, was there a surgical site infection post-surgery, or did the patient stop vomiting after a particular medication? Or maybe you're reading the news and want to reason about what happened, right? So how many Iraqi civilian casualties were there in the first week of the US invasion of Iraq, right? So some quantitative reasoning with the temporal reasoning, right? And you need that information in order to be able to come up with the answer. You need it in some form. We don't know what form. and it can get pretty tricky. So if you look at this last example, right? So East German border workers began dismantling the Berlin Wall at the historic Brandenburg Gate on Thursday night to make a new crossing. So when did the Berlin Wall fall from this? The answer is Thursday, right? So there's some inference that has to happen. But you have to start with something simple, right? You have to start with some basic understanding of the events and times. So here's a toy example. Here's a blog, February 18. Yesterday, Holly was running a marathon. When she twisted her ankle, David had pushed her. And so you get a temporal graph that looks roughly like this, right? So this is today, this is the day before today, and then during the day there was a run, also known as the marathon, and then there's a pushing and the twisting, and the pushing happened before the twisting, presumably, and so forth, okay? So, and you can imagine people asking questions like, okay, well, did Holly keep running after twisting her ankle? What kind of information do you need to answer that, right? This is just from common sense knowledge, which you get somewhere, maybe from an immense amount of corpora you've pre-processed, and then the text, okay? So very commonly, solutions to this type of problem involve people processing the text to detect events, processing the text to detect times, normalizing the times to some ISO standard, and then do pairwise classification and label the pairs with the appropriate relations. So before, after, during, and so forth. And then, of course, you run into problems because you get this time graph, and there could be cycles in the time graph, and so there's conflicts that you have to resolve, and they're typically resolved on some sort of ad hoc basis, relying on some confidence scores for your relation assignment in your classification task. So because in many cases temporal relations are non-local, right? So you take a newspaper article, right? And there's a long discussion about some events. A lot of the relations will be non-local, right? So because of that, for a very long time, literally until like last year, there were no deep learning solutions to this problem. So we did a very simple model that dealt with non-local dependencies by looking at dependency paths between the two entities that we're trying to classify. I'm not going to dwell a lot on this, but basically very little by virtue of input except for the dependency parse. And you feed into two RNNs, the sequence of tokens on each dependency path up to the least common ancestor. And then you output a probability distribution over your relation categories, right? So very similar to what other people have done, except super uniform treatment of all the entities. All you need is a parse, and that's it. So we tested this on a corpus that basically had, you had to generate some markup of input text, and then based on that markup, a standard QA system was supposed to answer some questions. And so this very simple system did pretty well. So T, temporal information extractor, is our system. And if you look at the percentage of correct answers, we beat the previous soda reasonably by doing very, very little engineering for the model. So we also tested it on one of the standard benchmarks for this kind of task without modifying our architecture completely. And architecture was modified for the QA setup. So, but on this intrinsic task, we got state-of-the-art also for free, which was nice. Okay, but we didn't really resolve the main problem. And the main problem in this type of task is you get these conflicts, right? So you have individual models that classify different types of pairs of entities. And then you combine them, you have to run transitive closure on your temporal graph, so that if you have something like A before B and B before C, you want to be able to derive that A is before C, right? Because your reference might have that relation and not those other two, okay? Because humans are also human, and so when they do the markup, they miss a lot of relations. They're not going to be able to do n-square relations, right? Okay, so when you do this type of model, you run into these conflicts, and then you have to use some heuristics to resolve these types of cycles. So, for example, you eliminate low probability scoring in some order, trying to optimize some scoring on the full time graph. Okay, so we found this fairly unsatisfactory. So mostly because, as we know, right, when humans read text, they don't actually locally order event pairs and then form this global picture of the timeline that reconciles the conflicts. We don't do that. So instead, what we do is we basically process relevant pieces of text, right, and understand the relations and store them somewhere. And then we refer back to what we already learned to resolve relations that we see later, right? So effectively, the idea is we store some kind of contextual representation of relations we already read about, and then use that to resolve whatever comes next, right? So the question is, can we emulate this process? And so if you've been paying attention, you'll know that there's been quite a few models introduced in the recent years that have some sort of capacity for this global memory that's outside of LSTM type units. So the first and the more famous one is the neural Turing machine, but there's quite a few other ones that have been, well, I should say under 5 main ones that have been proposed mostly for non-language tasks, and they haven't really been applied to language tasks. Again, with the reason being that it's fairly hard because of the discreteness of the language input. But basic idea for these, if you haven't seen them, actually, why don't you guys tell me how many have seen neural Turing machines? Okay, some of you. All right. So the basic idea is you have this global memory, right? So you have your standard recurrent setup usually, and at each time step you do something. Typically, you would read from memory and you would write to memory. And you could do this using an attention mechanism. And if you remember, an attention is just basically you're computing a vector that's going to give you a distribution over different memory cells. And you're usually computing it from your hidden layer or some cell state or whatever it is your recurrent architecture does. So you compute a distribution of memory, and you read from it. The output of this read operation is provided as input to your recurrent model together with the actual input that you get at that time step. Okay, so that's the so-called soft addressing. There are also versions of this that use so-called hard addressing, where instead of a distribution over the full memory, you get a particular address in the memory. And the problem with that, you can't really do the standard backpropagation with that, so you have to use a reinforcer algorithm to do this. But people have tried both, for example, with DNTMs. Anyway, so none of these architectures really have been used successfully with any real NLP tasks. I believe, I forget, either TARDIS or DNTM was applied to Bobby. And I think the bragging rights were that they were able to do coreference well. But again, it's not really a real coreference, right? It's this toy corpus. Okay, so our solution was this similar kind of model with some important modifications. Again, the idea is to remove this very hacky and unrealistic thing that you have to do for these types of tasks. In other words, this weird post-processing where you reconcile your results in order to factor in long-distance information, right? But instead, integrate global information into memory. So we call this model global context layer. It does what basically I told you about, which is we have this memory component, and it has attention-driven addressing mechanism. And it keeps an updated representation of the full context as pairs of entities are read in for pairwise classification. So the model reads in the pairs of events and temporal expressions, and then saves some information about each pair into the memory, and then reads from the memory at the next step. So this is the overall architecture. So the backbones of this are similar to the architecture I just told you about. So we have, the left branch and then the right branch. These are parse branches that are read in by LSTMs. Some hacky stuff to put in the time values and types. So this part, not the point, but this part of the model is basically what we had before, except before we also had a pruning algorithm that resolved the conflict. But now we won't have it. So instead, in addition to processing the dependency paths for each pair, remember we had dependency paths to the least common ancestor fed into the BiLSTM branches. So now we're also going to have flat context around each entity, and that flat context is going to be used as keys by which we're going to retrieve from the memory some information about this pair or similar pairs if we have seen them before. Okay? So now we have these two additional BiLSTMs reading in the flat context for each of the entities in the pair. And that's given to the GCL controller, which could be anything. We used a stateless controller and an LSTM controller, got roughly the same results. So the controller uses these embeddings produced by the BiLSTMs for the flat context to do lookup in the memory, get from the memory whatever was saved in that location that is most similar to, or the locations that are most similar to this particular pair of contexts, and then use that as additional input to the classifier for that pair. So just to walk you through this, there are two sets of inputs for each entity pair. There is words and context window around the entities. These are used as keys to do lookup in the memory. And there's shortest dependency paths between the entities on syntactic trees. So these are together with the previous input fed into the classifier. So then context for each entity is processed by an RNN layer. We get a unique representation for each entity mentioned, which is going to be used as a key. Dependency paths together with these are fed into a pairwise classifier, producing an embedding that has some way of capturing this temporal relationship, right? So we know this because we just worked with a model that used this exactly to do the classification, right? So now this embedding that's produced by reading in the dependency paths, along with a hidden GCL state at the previous time step, and the contents retrieved from memory, are used as input to the controller network, which produces the output layer and the classification, and also updates the memory. Okay, so following this scheme pretty much. Okay?
So all of this scheme is
Sorry?
all of the, what you show is just a single cell of the
Single cell? How do you do this?
cell.
So you have,
Just a single time step.
right, so you have your controller network, right? It doesn't have to be LSTM. All you have to do is provide these inputs continuously to it.
I mean the softmax here is what do you repeat this multiple times?
Yeah, so you feed in pairs of entities in narrative order, right? So you start at the beginning of the text. Does that make sense? No? Okay, so you got the keys, you got the relation embedding, and you got the output of the controller that's written to the memory for the current pair. And we use the same attention for the writing and the reading at each time step, obviously. There's some other machinery that I'm skipping here, which is not necessarily essential, but so there's some sharpening of weights during the addressing, using the addressing mechanism, and there's some other stuff. But the basic idea is this, right? So the main difference between this model and the other models I just flashed on the screen is, if you go and look at DNTM, for example, you'll see that they actually train, their addresses are trained weights, right? We don't actually do that. What we do instead is we train a model that will compute the keys from the entities, right? That's it. So the key that's going to be used for each input is going to be different every time. So essentially, we have this associative array that's indexing memory on the context for each entity, which I think is really cool, right? Because if you have entities in similar contexts, presumably you're going to get information about the pair that contains similar context, right? So that's the key here. And so your memory consists of these keys and the corresponding memory slot. So this is roughly what it looks like, right? So you get the input entity representation, and you get the input content representation, which is computed by the lower portion of the model that computes an embedding for relation, right? The controller gets it, right? The controller computes this attention vector, right? Which is based on computing the similarity of the key pair to the key pairs in memory. And what we did here, what I skipped here is basically you compute them for entity 1, entity 2, and you also flip them because you don't know in which direction you saw these similar entities before, right? So you compute this attention vector, you do the read, you produce a context representation, right? So this is your read from the memory, and then you feed that into the controller together with the input content, produce the output, and write it back to memory. And repeat, okay? So you do that in a sequence, but basically we did this was a bidirectional read, so we read pairs of entities in both directions. And there's some, as you might know, if you try to work with these types of models, they're fairly difficult to train, so this kind of model can be trained from scratch. It's typically slow to converge. So the trick that we did was we pre-trained this relation classifier and then continue training it with GCL, okay? So that means that the embedding X for the relation was basically all set by the time we start training the GCL, okay? Okay, so this embedding is very close to optimal by the time we started, okay? Okay, so here's the results. So the lower part has the GCL results with different types of controllers. And keep in mind, we're not doing any post-processing or pruning, right? So basically the work of the post-processing that the upper models were relying on up there is done by the GCL, right? And we're not really beating these baselines by that much, although for this type of data, that tends to be a reasonable publishable margin for whatever reason. But the idea is we're getting very similar results with doing virtually no post-processing, which means this memory component is actually doing its job, right? So what I want to emphasize here is that I think the cool part here is that if you think about the discourse coherence, not for this task, but for any other task, for the same dialogue generation task, you want to have representations of entities and information about these entities stored, right? So this type of architecture actually allows you to do that. We create this unique key based on the context input, and that's what's used to retrieve information about the entities. And yeah, here we're using pairs. Ideally, we want to use a representation for a single entity, and figure out how to compress what we need to know about it into a single memory row. But the lookup mechanism, I think, is what you really ultimately want in your models. All right, so I think we're almost done. So these are some general conclusions. For the memory-based, memory-augmented neural network type of models, what we really want is this global updatable memory that can do something different than what I've just actually told you about, right? And the difference is, here I'm still using my memory, maybe in the right way, but to learn from one task, right? So what we want to do next, the next step is we want to have a model that is able to retain these representations, right? So we want to move away from these specific things that we're training our models to do. We want to have a mechanism that allows us to save some sort of memory state, to access it in some way, maybe through convolutions, maybe, we don't know, right? But there's got to be multiple ways of accessing this memory and saving the information in it. So, we don't want to read in and use existing sources. Instead, we want to be learning from the input, right? Have a mechanism for storing the input and retrieving it. Have a mechanism for activating the relevant parts of the stored information, right? So storage and retrieval for long-term memories and also short-term activations. And that presumably should allow us to interpret the input naturally and keep the discourse coherence locally and resolve long-distance relations. And that's what presumably is going to allow us to do this generalist NLP that we don't currently have. All right. That's it. Thank you. Oh, and these are the people that actually do the work. We're also hiring. If you're interested, talk to me. So, questions? Yeah. Yeah, go ahead.
Thanks for the talk. I have a question. What is your estimate in time, in years maybe, when some kind of system with neural memory will come to production?
Good question. I mean, I would like to think it's going to be earlier rather than later, but we don't have anything close yet, right? So I always give this example, right? So I have a 2-year-old son, and he's been training his neural networks for 2 years, and he still barely speaks, right? We expect our models to just learn it like that. Like, we'll train for a week, and we're like, oh, this is so long. But most importantly, we don't have a general mechanism for this stuff yet, right? So I think if I'm being optimistic, I'd say 5 years. If I'm being pessimistic, I don't know, 20. You have a question?
Yeah, how many entities we solve for?
So these are fairly long sometimes. So the length of a text in this data set, it's called time bank dense, varies quite a bit. These are news articles, so some of them are pretty short. Others are, like Associated Press articles, which are pretty long. So it varies, and there's some trickery in the way we train it. So we pick the pair order and subsets of pairs to do this. So we don't, for long text, we don't fit necessarily all the pairs, right? So yeah, I mean, I can't tell you right now what the size of the batch of pairs is that we trained with. It's not super small. I'd be guessing on the order of like 50 pairs, maybe something like that. Which, if you think about it, if you think of a text and a bunch of entities in it, it's a fairly large piece of text, right? So, other questions? Yeah.
Is it possible to use
this kind of architecture for task of transfer learning for the entity recognition, namely other recognitions? When you give some examples of entity, so it's like 20 samples of some entity, and you want your algorithm to find the same type of entities. Is it possible? So you keep in memory the examples, you try to match contexts where you find these entities.
So you could probably adapt this, right? So you'd be doing lookup on context, right? And you'd want your model to generalize from context in some way. But probably for entity recognition, this would be overkill, right? You don't need this kind of memory for just.
No, I mean, if we don't want just like a named entity, we want in dialog system to recognize
Entities.
different entities for slot filling and so on. For every specific domain, we have a specific set of entities. And so can we have a general algorithm which can be easily fit to any domain, given some examples of entities we want to recognize?
So I'm not sure about examples of entities. I think the more natural task for this would be global coreference, right? Because really what you're doing in global coreference is resolving these, you have the entity representation of some sort, right? And every coreference system would have that. It's just it's not learned in the same way. So technically you would have this set of contexts that you're going to be somehow recording into memory together with some information, and then looking it up as you read in entities. So we haven't done this yet. But I think this sort of the coreference is the more natural way of doing coreference through memory would be like entity by entity lookup, right? So instead of using pair lookup, you use single entity lookup. But then you have to make sure that you have enough information in your memory that allows you to disambiguate, right?
Any other questions? So I think it was a really cool talk with very nice and great ideas. I like the first one very much, and the second one also I think will be helpful in our project too, because we are thinking about planning and memory, and it's relevant to this part of the general system. So let's thank Anna